Thank you. Thank you very much. It's a privilege to speak at this great conference, and it's actually very sad. It's sad to me. So I knew Andrei for 37 years, and always enjoyed him as a mathematician, and maybe even more as a personality. So I knew him well as a person, and I learned a great deal from him from the very first time I saw him. For example, he was doing his work on representation symmetry group, and that's the way how I learned representation zero symmetry group, and many other things. So when Andrei was doing mathematics, he was doing this kind of very clean way, and in the way where, I mean, it makes it very easy then to learn the subject from him. I just want to give one example, which is not my opinion. So I was trying to learn a few years ago very exciting subject about periodic representation of periodic groups. Then I understand that I can't do this and it's kind of mess. And so I asked Sasha Belinson whether he can comment on that. He said, yeah, it's a mess. But the same mess was in representation theory of, the complex numbers of periodic groups before the paper of Joseph Bernstein and Zelevinsky in 1976 appeared in SERS. Was the same mess. Just nobody to clean this up now. So, and like I say that mathematicians are kind of lucky because we live in a society which is very rich of remarkable people, one of whom was Andrei, and we have kind of lack of meeting them, talking to them, but we not always use this wisely. So, for example, the subject of my talk today, I had in mind talking to Andrei about this, because this is directly continues his work. And I kind of postponed this again. I lived just 3 hours of drive basically from his house. I said, okay, so I will come to Boston. First of all, I thought I will come to MSRI. Didn't happen. Then I thought, well, I'll come to Boston. We'll speak on the conference. And then it's too late. So I'm going to talk today about a subject which is joint work with Linhui Shen, who is sitting here, just there. And its title is something like Configurations Potentials, and many other things which come after that. And as I said, it's a kind of continuation of the works which Andrei was doing. First of all, in 80s, Israel Moiseyevich Gelfand and Andrei were thinking about the problem of like multiplicities and tensor products. And they had an idea that the answer should be given in some beautiful form of some polytope, which, so you take integral points of this polytope, and then you get the weight multiplicities. And this did happen, and they had a paper on this. Then there were papers by Arkady Berenstein and Zelevinsky, which get to this famous BZ patterns, Berenstein-Zelevinsky patterns, where they understood this in a kind of different way. So for SLN, it was a very beautiful polytope, which Gelfand and Zelevinsky produced. Then there were lots of other developments. One of the most remarkable was Knudsen and Tao. We were talking about this, who looked at this and discovered yet something very beautiful about this. So I'm going to somehow continue this line. It's a very rich subject, and I hope to contribute a little bit to its understanding. So let me start. So let's suppose that we have G, which is split reductive group over Q. And actually, I can assume that it's semi-simple, or just that the semi-simple part is simply connected for certain applications, but usually it will not matter. And first of all, there is a flag variety. As just the collection of all Borel subgroups, and it's isomorphic if you choose one of them to G mod B. And then there's what is called principal affine space, is denoted by A sub G. It's called principal affine space. And somewhat misleadingly, it can be written as G divided by U, where U is maximal unipotent. What actually it is the following. So let's suppose, first of all, that we take the adjoint group. So, this is G by center. Then the space has a nice interpretation, which is very important to me in this talk. So I can say that in this case, this A G prime is a moduli space. It's just like a flag variety. It's a collection of pairs, unipotent subgroup. In G, and like in Sasha's Braverman talk this morning, that's a character of unipotent group, which is maximal, non-degenerate. So let's just consider the set of pairs like that, U and chi. And so the group G prime acts on these pairs by conjugation. And by definition, this is a G. And now this is isomorphic to G divided by U. And so why this is misleading? Because if you want to know what this U stands for, it actually stands for U and non-degenerate character. So if you want to specify a character, when you say U, you mean U with spinnings. So you mean all root data already given to you. Only then you can associate to this guy. Otherwise, you don't have the character. So it's really the set of unipotent subgroups and characters, principal affine space. And if it's not adjoint, you can understand it still this way as G mod U. And what's important, the only important thing for me, is that there is a canonical projection to this guy. And this guy we understand. OK, so the conclusion of this discussion is, and I want to emphasize this again, that if somebody gives me an element of this principal affine space for G, not necessarily G prime, then I can assign to this canonically character chi. You can call chi sub I from the unipotent group UI to A1, which is parametrized by this element. So we call them decorated flags. All right. So now I can introduce. Oh, this I should not. So this is. Let me. This is joined. I remember Gelfand taught us that if you work with cursors, the name of the cursor should stay for the whole lecture, not from the beginning. Not only for the beginning of the lecture. So potential. First of all, sorry, I went a little bit ahead of myself. So first of all, I want to introduce the main object, conf n of A. I will write AG. I will call it also A, just when G is not, is kind of not obvious. So this is just A to N divided by the diagonal action of G. That's a configuration space. And so what's important about this, it's a kind of theorem, and it has canonical positive structure. Cluster actually, but that's important that it has canonical positive structure. So this is a theorem which we proved with Volodya Fock. And it also goes back to some works of Fomin and Zelevinsky, which we use. It's again, in particular, relates to work of Andrei. So it's important to me that it has canonical positive structures as space. Now I can introduce the function on this space, which we call the potential, which plays central role. It's a function on the space of configurations of n points in the principal affine space to, I said function, but I mean a rational function. It's not regular. can think about as a stack. So I usually need just its generic part. So I will use this in different ways. So when I said it has a positive structure, when I formulate a theorem, it's only important that you take generic part of the stack, and this is nice algebraic variety, which I again treat only up to birational isomorphism. Basically, just need generic part. So it depends on the context we are, but for a big part of the talk, this context is enough. So you have a rational function here, and I want to define rational function here. So let me define. So first of all, how I think about configuration of n flags, decreed flags. So I draw some kind of polygon and put flags here, decreed flags, elements of the principal affine space. Now let me write down the formula first, then I explain that this W is given as a sum of the contributions which come from the vertices, and I will define them in a second. And so at every vertex, I will define some kind of unipotent element here. This will be U3. And then apply to this element the character which corresponds to this particular decorated flag. Now, how do you do this? So you have this picture. For example, let's take this A3. So you have here, let me do it in general, take AI. So take here the flags, but I will project to the usual flag. So I use a notation that the BI is just the flag corresponding to AI, because there's canonical projection AG to BG. So I can always associate the actual flag to a decorated flag. And so I take those flags, BI minus 1 and BI plus 1. And now it's a very easy statement that generically, the way we picture is like that. Generically, there exists unique element, UI, which belongs to the unipotent subgroup which stabilizes this decorated flag AI, such that this element moves one pair to the other pair. So if you just take a pair, AI, BI minus 1, then you get the other pair, AI, BI plus 1. Now let's pay a little attention to that. So I said we have configuration of flags, but I of course start originally with a sequence, with a collection of decorated flags, I know by curly brackets, before dividing by the action of the group G. And just if you have a configuration, so you can do this for every vertex, you can move. The basic fact is that if you consider this A cross B, and then it has a unique generic G orbit. So if you consider here generic part, the part with the corresponding flag here and the flag here and generic position, then this is a G tensor, principal homogeneous G space. And therefore, if you have generic pair here and generic pair here, it's a G tensor. There's a unique element which moves one element of this G tensor to the other, and it, by definition, preserves this flag, a decorated flag. So we get this element UI. Now, the character which is assigned to this decorated flag knows its job, and it produces out of this element a number. And then we take the sum of all these numbers, so we get a function. That's it. So that's the potential. Now, to formulate the theorem about this. No, not at all. Brackets here means that I take a collection, and then I say that obviously the function I got is G equivariant. You see it? Yeah, it does. It's very important. Yes. No. It's by construction evidently cyclic invariant. Yes, by definition. That's a very good comment. Now let me remind some general facts which I'm sure in this audience are well known. So let's suppose that you have a positive space. What is a positive space? it's a space which is a rational variety and has lots of coordinate systems, and these coordinate systems are related in a subtraction-free way. So let's suppose also that you have a function on this space, which is a rational function, which is a positive rational function. Which means that at every coordinate system we have on the space we care about, this function is written with the sign pluses. Basically, you don't have use minuses. So if you have this setup, then you can do two things. First of all, you can associate this to a set, two sets actually. First of all, we have a set of ZT tropical points associated to this. So that's a set. And then you have a subset of this. And this is the one which I really need. Let's call this X sub W of ZT plus. This is a collection of all points L in the set, in the tropical set, which has a property that the tropicalisation of my function and this element is non-negative. Needless to say that a function on this space produces you a tropicalized function, VWT, which goes from X of ZT to integers, and then just cut the set of your tropical points by this function. So, if you combine all this knowledge, the fact that conf NA is a positive space, the fact that W is a positive rational function, then we end up, so conclusion, we get some set, which I just need a notation for it, called conf n plus a ZT. So z of positive tropical points of this space. Now, let's look what happens in the simplest possible examples. So if you consider the situation when n equals 2, then you have space conf2 of A. And one can obviously see that this is birationally Cartan group in a canonical way. So this is the Cartan group. This means that if you tropicalize, it's obviously positive space. If you tropicalize this, and its tropical points, by definition who they are co-characters of this guy, which has a name, which is a lattice of coveights for the group G, or lattice of weights for the dual group G. So now, let's suppose that you have not 2 flags, but 3 flags. So look, so we have this many flags, conf n A. So if you look at this polygon, this means that to every ordered side of this polygon, you can assign this coveight. So we have the coveights, and so we get a map of this tropical space set, to be precise, to P to n. This is from the sides of the polygon, from this invariant. Now, we actually have inside here, actually, I think I made a mistake. I said P is a set, is the lattice of coveights. I didn't say they're dominant. I'm now going to introduce the dominant coveights and claim that if you restrict now to the set we introduce, then it maps to P plus. So this means that if I have any element of my set, this one, what? For n equals 2, this does not imply. This n is now is bigger than 2. You're right, so I need to assume that n is bigger than 2. Yeah? Huh? This is also right. I mean, I can define another function which will give me exactly P plus, but I don't want to do this. So now I take really n bigger than 2. And so we get land here. And now we can use this, we can somehow, the fibers, this map, so if you take here point lambda, which is lambda 1, so on lambda n, living here, then we can have here this subset, which also is a little complicated notation, but deserves to be somehow denoted, lambda bar. So sitting here, which is just projects to this chosen collection of fundamental coveights. Okay, so now one can formulate a theorem which says that that's exactly the set which parameterize multiplicities and tensor products. Theorem. So conf n a plus of zt parameterizes. I would say canonical basis, but I'm not going to discuss what means canonical because there are several of them. I mean, some particular basis which I'll introduce later on. Canonical basis in the following. So you take finite dimensional representation. So first of all, it takes the Langlands dual group GL. Now the collection of the coveights here becomes the fundamental weights of that GL. So you can take the tensor product of the corresponding representations, take GL invariants, it's finite dimensional vector space, and so the theorem says that there is a canonical basis which parameterized by the same set. Now, yeah, there will be a construction. It's actually, no, it say much because the set on the top is a finite set. It says that the cardinality of that set equals to the dimension of that. That's a non-trivial statement. For n equals 3, yes, that's a non-trivial statement. And also, the way I formulate it, it's manifestly cyclically invariant description because, as Sasha was pointing out, by definition of this construction, cyclically invariant on the nose, manifestly. And so this set of invariants known to be should have parameterization cyclically invariant, but usually you need to work for this if you're not outside of GLN. But in this presentation, it comes by definition for GLN. Or Knudsen tau, which is a consequence of that. So for GLN, you can do this in a cyclic invariant way. The Berenstein, I mean, I mentioned at the beginning there was work, I said, Gelfand and Zelevinsky, and continued by Arkady Berenstein and Zelevinsky. And they produced some kind of description of this set. They were doing this. So this was Berenstein, Zelevinsky, which is any G, which is important, and they did n equals 3. Of course, somehow you can deduce the general case to n equals 3. It's sort of enough to know this tensor product multiplicities. But again, this answer comes in the completely symmetric way, which is kind of new feature of the whole of this. And okay, now. What was the second? Sorry.
If you have a tensor product
Yes.
representations of quantum group and you want to make a cyclic permutation of vectors,
Yes.
then the usual obvious map is actually a more obvious representation.
I mean, it definitely relates to quantum groups because it also gives quantum invariance, but I'm not sure I can say yes or no to your question.
I mean, for invariants. So if you have invariants, there is this break.
Yes.
It's kind of complicated, but the cyclic permutation is the
Exactly. Yes. That's exactly the point. Yeah. So the cyclic is the one you should care about. Okay, let me reformulate this result. It's nice to reformulate in many different ways. In particular, later on explain to relation to honeycombs of Knudsen and tau. But right now, I just want to look what this means, as stated. So let me recall the very basic fact discovered by Elie Cartan and formulated, I'm not sure, maybe by Gelfand this way. I read this in the paper of BGG in the introduction, that O of GL is actually the set of the space of regular functions on the principal affine space is direct sum, is a model, is direct sum of all finite dimensional representation, each counted exactly once. This is just Elie Cartan's theory of highest weight. Huh? I mean, this is a Cartan's theory of highest weights. I think it's Cartan, right? Anyway, so it's long ago. So then what we did, so if you look at this, so we defined canonical pairing. So we take a set, which is the set of configurations of n points in this decorate flag variety principal affine space for the group G. We considered the set of tropical points, and we cut it by this potential. And then we paired this with another space, which is exactly the same space, but for the Langlands dual group. And so what we did, we just produced a single function. So you can call it I. So that's what things like that we call with Volodya-Fock and some related conjectures canonical pairings. So we produce canonical pairing between this set and this space. Why this is so? Because direct sum of all tensor products without GL is obviously by definition the space of functions on A, GL to N. And if you put the configuration spaces, means take modulo G, this means that you are down to the invariants under the group here. So it's a tautological statement. No, I read this as follows. So I have a set and I have a space. I take a product of a set and a space. And on this feature, I have a function. You can specify this function to any element of this set, and you get canonical basis. But I don't want to think about canonical basis just as a basis. I want to emphasize that the space it comes from, and actually the stack it comes from, is extremely important. And so this is this way, but you can also read it the other way. Yeah? Sure.
I can actually understand. This is very important, I think.
Yes, absolutely. Thank you very much, sir. So if you take, I'm always glad if somebody asks, so I have an excuse to go slowly. So if you just take functions here, this is by definition tensor product of GL, tensor and so on, tensor of GL, right? It's just a product of the spaces. And now this, as we know, is a model. So this is direct sum of V lambda, tensor, and so on, tensor. This is direct sum of V lambdas, where lambda belongs to this P plus. Right? Yeah? Now, if I want to put here invariants, I can still do it. And so I have invariants sitting here. Right? But that's exactly the space which stands in this theorem if you take the sum over all lambdas. I'm sorry, I formulated actually incorrectly. Nobody, even Sasha didn't correct me. So you have to put here this lambda. So this is a subset which is a fiber over lambda. This is a finite subset. And so this finite subset parameterizes this basis in this finite dimensional vector space. But if you take the sum over all lambdas, then you will see that this big set parameterizes a canonical basis in the whole thing, which is by definition the space of functions here, which I can interpret this way. So this is O of conf n of AGL. And so what we produce a map from a set to the space of regular functions, which is a canonical basis. I interpret this way. Okay? Yes?
So we said that you're thinking about a configuration space in invariant.
Yes?
I think that's what this theorem tradition is literally true. You really sort of need to think about it.
Great point. Great point. So here it was birational. Here it's a stack.
No, I mean, I'm talking about the tropical part.
Tropical part is entirely birational.
What do you mean?
I mean that if you have a positive space, it is a structure which depends only on open part of what you have. And if you have a rational function, you want me to define positive space and its tropical points? All right. I think you have one of the definitions. I mean, I don't. Okay. I don't understand you. Why do you ask me? But okay. All right. So what I mean here is the following: that first of all, I have some torus, and I have a map from this torus to the space I consider. And this, I have a collection of these maps, I alpha. And this map is by rational isomorphism. So I have some rational space. I have some parametrization of this space by split torus, which means that I have such a map, which is by rational isomorphism. And the condition is several conditions. Most importantly, that we have one tor like that, I call it T alpha, and another tor like that, T beta, which goes this way. But if you go like that, you get a birational map from this tor to itself. Let's call this map, I don't know, phi alpha beta. And the condition is that if you write this map phi alpha beta and look what it does with any character, it produces you a function, rational function, which is sum of characters divided by some other sum of characters. Okay? Now, tropical points is a set. So if you have anything like that, you can define the set of tropical points by saying that you have these sets, you have the co-characters of these T alphas. Each of them individually is isomorphic to Z to N, where N is the dimension of this space. And now, but this isomorphism is, it depends on choice of base of characters here, but you have many of them. Now, if you have this guy and this guy with T beta, then there's a tropicalisation of this birational isomorphism here, which produces an isomorphism of sets, because it's both way positive, for example. Yes? Now I said that the tropical point, it's an isomorphism of sets. Because the map exists and the inverse map exists by definition, and both of them positive rational maps. Therefore, this composition is the identity, and therefore it's an isomorphism. Okay? Now, by definition, a tropical point is a collection of points here, L alpha, in each of them, which are related by these tropicalized transformations. So, in simple terms, a tropical point means that for every parameterization you have, you choose a tropical point, means co-character, and then if you go to different charts, they have to be related by piecewise linear transformations. And you know this definition, right? All right. So, now, let me return back to this canonical basis. So this is like Gelfand and Zelivinsky dream, because they wanted to have a polytope, nice polytope, which parameterized canonical basis. We have it here like that, but it's not exactly polytope, because in the case when this space has some nice, beautiful, unique coordinate system, which is one is better than the other, we would get a polytope, because we would get Z to N and cut it by some inequalities. This would be a polytope. And this would reproduce for GLN, and N equals 3 is this what Gelfand and Zelivinsky were doing, what Berenstein and Zelivinsky partners were doing, what Knudsen and Tau, their hives, it will exactly the set. The reason is that for GLN, there is a distinguished special coordinate system, which we construct with Volodya-Fock, which does exactly this. It produces the hives of Knudsen and Tau. I'll say this precisely a little later. But I just want to return back to the work of Andrei and with many cursors for like long period of time. So for GLN, it's a polytope, yes. But not for GLN, it's not quite polytope. It's a set of tropical points in some space. And what I want to emphasize is this space is not less important than the polytope. So now let's get to this point. So let's consider this duality. Let's read this in another way. We can say that we also have this pairing. And that's a completely different thing, because this is a canonical pairing for G, and this is a canonical pairing for GL. What's nice here is that the spaces are exactly the same. And so what you really say that you have this pair of spaces. And actually, this is the same space, just for different Langlands dual groups. And it's tempting to say that what you really want to consider, you want to consider conf n ag, and you want to consider conf n agl, and you wanted to have something which says that these two spaces are in duality. And so what you see in representation theory, you see the two tropical limits of this duality, because you can go, tropical limit means that you go to the infinity positive part of the boundary of one of the spaces. You have two spaces. Yes. Just Sasha, you calm down. So I have two spaces, and I want to have some kind of relation between the spaces. Now, as Sasha is saying, we have here functions here and here. And so what you would like to say is a kind of mirror conjecture that there exists a mirror duality. And I'll formulate this in a second, which is exactly about this guy, so to speak, about this pair of spaces, which tells you the actual duality between two spaces. And what representation theory tells you the limits of this duality. Now, what do we mean by mirror duality? Let me stop here for a second and explain how this potential actually used. So, mirror. Well, the structure which we have here is the following. First of all, how you think about this pair of spaces. You draw this kind of picture, and you put here flags like A1, A2, and A3, and then you do a different kind of picture. And you put some other flags here. It doesn't matter how I call them A1. What's important that when they're sort of orange, they're on the dual group. And it's important that they're located like that they really kind of rotated. And so this is how I think about this product of these two spaces. Now, the data which we have on this is the following, that first of all, the group H to N acts on one of the spaces, conf NA. The group H Langlands dual, oh, sorry, not this way. The other space, conf N of A GL, maps to H to N Langlands dual. And let me call this map called somehow lambda. Oh, lambda, maybe not great notation, mu. So, so we have this pair of actions. Now, how they come? So if you look at the configurations of the first type in the group G, you can rescale the flags because there is this well-known action. So the group, Cartan group X on the principal affine space, traditionally from the right, although it's commutative, doesn't matter. So that's how it acts here. On the other hand, I explained that you have it's no longer visible. That you have a map that here, whenever you have, I write it again, conf 2, let's say, of AGL, there is a canonical rational map to the Cartan group. And so here, you put the Cartan, so to speak, AGL. And now it's sort of OK, because you map to Cartan group sitting here, and you act by the Cartan group of the dual group sitting here. But these two Cartan groups obviously talk to each other because they're physically located in the same place. This place is here. And so you have this kind of dual pair of actions. Now we can play the game. I mean, again, the mirror duality means many different things. And we hope that here the situation is very good, like all of them happens. But let me just formulate one thing which you can do with this picture using all this positive geometry. You can write down an integral. We can use this potential as Landau-Ginzburg potential. So now the point is that omega is Landau-Ginzburg potential. And in particular, following Giventhal, Giventhal was first to write down something like that, I believe, when he was proving mirror conjecture. So what you can do, you can write down integral. So remember, you have this map. I called mu. Now you can integrate exponent of minus potential divided by the Planck constant multiplied by the cluster volume form. Cluster volume form. It's a general fact which actually, for example, we use in different businesses with Volodya when doing this representation in Hilbert spaces. It's important that you have canonical volume form, cluster volume form on this space. So it's volume form with logarithmic singularities. Now you can multiply this by function and integrate. Now integrate where? So, I didn't even say it will be a function of what. So you get some function f of t, and now t belongs to this. It depends on which side. If you're on dual side, AGL to n. Let's just take here positive points to be concrete. And so remember that we have this map called mu from conf n AGL. It goes to HGL to n of R plus. And what now you can do, I mean, you have map of positive spaces, but I can immediately pass to the set of the positive points and have a map like that. This is my kind of mu made it real positive map. And so I want to integrate this function over the fibers of this map. So I use the projection to the Langlands dual Cartan to push down my potential times the volume form. Now, what's great about this is that usually integral can be horribly divergent. But here the function omega, the function w is positive rational. It's positive rational. And therefore, if you take w restricted to the positive part of your space, conf n AGL of R plus is the most important here, then this function is at least non-negative. And so you integrate here e to minus number, which is non-positive, divided by a very small number. And so integral doesn't converge 100% because you can have directions where it's just constant, and then you integrate constant over line. But it's very close to be convergent and can be made convergent. I mean, one shouldn't worry too much about making this convergent. Or if you don't want to play this, you just take the d model which corresponds to this integral and just play with the corresponding d model. So you have a function. Exactly, yes. So let's write it down. Yes, and I'm answering this question. It's inverse of mu inverse of t. Again, this inverse is not exactly convergent on the nose, but it's very close because it's integral of something which is which is smaller or equal than 0. Okay. So that's what happens on the one hand side. So on one hand side, you have this projection, and you can write down this function. And as I said, I should write this down. This is like Giventhal potential. And it's not only like, it's actually, in some situation, will reproduce Giventhal's potential precisely, but it's not exactly the one I'm talking about here. Now, on the other hand, and I don't want to spend too much time here. So on the other hand, you can think about something like quantum cohomology here. So in the end of the day, this is going to produce some DH model. This function satisfy. H is the same as there. And one can conjecture that this DH model is the same one which you see on quantum cohomology. You can call it quantum equivariant. Floer cohomology as Giventhal does. But it's supposed to reproduce the quantum connection on the dual side because, just a second. Now, what I have here, I can take any character chi of Hn. Now, it produced me a line bundle L chi, which is line bundle on the configuration space of endpoints in the flag variety, because configuration space of A maps to configuration space of B, and the fiber is precisely H to N. That's this action. And so if you have a character, you produce a line bundle. Now, if you take map which has chased to chi C1 of this line bundle, it lives in H2 of this conv. And so in the end of the day, you get a map, the first Chern class, from the characters of H to N, Hg to N, to this guy, to the second dimensional cohomology. And then that's where the quantum connection lives, right? So you can look out. Yes, in B, not in A, in B, yes. So then you have here quantum connection D model, or if you brave DH model. And of course, the conjecture would be that this guy equals isomorphic to this guy. So the mirror duality here tells, so that's a conjecture, that this QH, whatever name for this, of conv and B isomorphic to this kind of f of t, or maybe just you write integral e to integral e to minus omega over omega, which understood as a D model. So this isomorphism of two D models. You can go forward, you can say that the function also makes sense, and so on and so far. It's a stack, so that's here, there's nothing I can do about this.
But the configuration N of B, it's not compact, right?
No, B is compact.
B is compact. The configuration space means that the points cannot coincide.
No, you take B to N, you divide it by G. It's a stack.
They can coincide.
Yeah, it's a stack, yeah, it's a stack. All right, so as I said, so I want to stop here talking about mirrors, because actually, you know, we have these potentials on both sides, and I just use potential on the one side, and one can play this game, of course, interchanging them, and one can try to play other games which mirror duality people play. The most sophisticated is Kontsevich homological mirror conjecture, which says that the category of, let's say, matrix factorizations related to the potential on one side is equivalent to the Fukaya category on the other side without potential. Or you can take the Fukaya category, Fukaya-Seidel category with potential on one side, and try to look to the category of equivariant sheaves on this stack on the other side. So you can play this kind of games, but in particular, you can write down this integral. That's somehow my main point, that this integral is basically well-defined, and that's very interesting invariant, which in this other but related situations produces solutions of total lattices by Giventhal and people who followed Constance Rich and Gerasimov, Ablazin, Lebedev were working on similar things and so on so far. And you, Sasha, yes? No? Okay. Anyway, so yes, GL2. Then it's then the.
You want to produce some sort of rational, some sort of invariant of configuration of 6 flags.
Why 6? I mean, whatever number of flags. No. This picture, Serge, this picture means that this is a duality picture. You have the orange guy, which relates to one space, and the white guy, which relates to the other guys. So you talk about 3 flags per time at the moment. They say that that something which happens on 3 decorated flags here is governed by the 3 decorated flags in the Langlands dual group on the other side. But you need to put them together to see that this really fits, because when I said that these D models coincide, it's important that the co-characters of one are characters of the other. That's the Langlands dual torus. And it's important that they sit at the same point. That's why I wrote this picture. They canonically, these 2D models, canonically live on the same space because of Langlands duality. Okay?
Maybe I'm wrong, but I thought you want some kind of geometric lifting of this pairing.
Yes.
Have you been able to compute it, or?
No, that's a different question, which we definitely don't want to go right now. I have like 10 minutes left, and I think the best I can do, I can explain how this relates to beautiful honeycombs and hive of Knudsen and Tau, and maybe I can say a word how this is proved. But so let me get to honeycombs, for example. So So Knudsen and Tau this was 98, if I am not mistaken, and this was following. So this was written after this great paper of Berenstein and Zelevinsky, which is 91 or what? Okay. So it's about 91 as far as I remember. Their story is the following. They said that let's G to be GLN. Then the Knudsen-Tau hives is the following data. So you take a triangle, and you consider what I would like to call the n subtriangulation. So for example, for n equals 4, you get something like that. This is picture, I believe, when n equals 4. And so now what you do, you consider functions f from the set of these vertices of this set, let's call Tn. This is n triangulation of the triangle. Two basically integers. Technically, this is 1 over n, if you want to treat some particular group and want to be correct, which satisfy this beautiful rhombus inequality of Knudsen and Tau. So if you have a rhombus, then, but as I said, this follows back to the description Sergei was talking about of Berenstein and Zelevinsky, and it was interpreted in a beautiful way, like honeycombs. So I just explain that point of view. So you put here vertices, and then you put that f of P1 plus f of P2 bigger or equal than f of Q1 plus f of Q2. So now if you put here some data, so for example, if you put some data here, which gives you this fundamental weights, and you consider the set of all hives, the set of all functions like that, which satisfies this inequality, that's precisely the set which parameterize multiplicity and tensor product. And I claim that's a theorem that given the special coordinate system on just conf NA for GLN or SLN, which we did with Volodya Fogg when we were doing this business on surfaces, then given this particular coordinate system, then this set conf 3 plus of a GLN or SLN or whatever you prefer put here is naturally, it's actually gives you exactly the Knudsen-Tau. Not something which is isomorphic, but it's precisely Knudsen-Tau. Literally. And actually, what it does, it produces some rational function which has exactly 4 terms in general. And that's the sum of these functions like that, this our potential in this particular coordinate system. Then you tropicalize and you get precisely Knudsen-Tau. And so I remember asking Chris Woodward when I first learning about this Knudsen-Tau, so I asked him, where did they get this? I mean, how you think about this inequalities? And he said, well, I don't know. There was this paper of Berenstein and Zelevinsky, and then was Knudsen-Tau. But how you get them? That well, Alan and Terry, they are geniuses, and they somehow invented this. And don't ask me. So, but there is some interpretation of that. Now let's look what it says in more general situation. Let's suppose that you want to do this on picture like that. And again, there is a theorem which Knudsen-Tau and Woodward now, which tells you the associativity. They said that if you have a similar picture here, and you can do Knudsen-Tau hives here, then this will be exactly the same as you're doing here. You can do Knudsen-Tau on this kind of grid, using this main diagonal of this main diagonal. And it's quite non-trivial theorem. It's like 15 pages showing that this set of inequalities goes exactly to this set of inequalities. Now, from the definition I'm presenting, this is obvious because, look, so if you take any polygon, for example, rectangle, so what you do, you have these flags like A1, A2, A3, and A4. And you can cut it this way, or you can cut them this way. But the character is additive. And so if you take character of this element of group and this element of group is the same as character of their product. And then you have this guy here, which is the same as sum of this. And the sum of two guys here is the same as this one. And just because the character is a character, you see that by definition, the W is the same here and here. It's true by definition, not by proof. But if you go into concrete special coordinate system, that becomes non-trivial theorem, not at all obvious. So, moreover, you can now place this not only on a rectangle, but you can place this on the surface. So now what we can do, we can take, for example, let me do this here. We can introduce a similar object on any surface. Now let S to be what we call a decorated surface, which means that this is a topological surface which can have some points on the boundary which we call special points, and it also can have a cusp, which means hole without special points, so something like that. And then whenever we have S like that, we have replacement. So instead of talking about configuration space of n points in AG, we can talk about this moduli space which we're doing with Volodya Fogg, we called AGS. This is some G local systems on S with some conditions at the boundary, and they actually twisted local systems, but they have positive structure as well. And so the claim is that this guy has potential, and this guy also has potential, always, for any surface. Now, why it goes very easy to explain, because the main property of the potential is cyclic invariant. It's invariantly assigned to the triangle, and it's invariant under the cutting of the triangles, as I just demonstrated, because this is just the additivity of the character. Now you can take your surface you like, triangulate the surface any way you like, and run the construction on the triangulation, and then the function you get is going to be independent of the triangulation. So it's well defined on the corresponding moduli space, which I didn't define, but which is kind of the right analog of this configuration space of points in the principal affine space. Then you have function, you have potential. You can define the set of positive tropical points here, who they are. Now the theorem is that this is precisely when G equals 2, when for GL2 or SL2, this is precisely integral laminations on decorated surfaces. As the notion of lamination is certain notion, and on decorated surfaces you need to do some kind of work which is not exactly trivial to make it right, but it was done. So there's a set of integral laminations on the surface, the way we define this with Fogg. And the theorem is that, maybe that's the last statement which I wanted to make, that's exactly what we get in this time. So for SL2 we recovered the notion of laminations. And for other groups, this is a kind of right generalization of this. And so it's kind of theorem when G is, let's say, SL2, the set of A GS plus of ZT is precisely laminations on S, and they're known to parameterize canonical basis. That's again going to our work with Volodya Fogg on local systems for the group, for Landau dual group, in this case PGL2 for the surface S. I emphasize here this is a local system. That's not the space we considered in the paper on duality conjectures. So this potential is needed to get from our X space to the local systems. And so the actual claim, the main point here, is that the duality I was talking about before, which I cast as a mirror duality, is actually duality between, let's say, AGS with potential. This is kind of mirror dual to the actual local systems for the Langlands dual group on the surface. And you can, as usual, you can place this backwards. You can place this the other way. You can put potential here, and then it will be this side. Okay, thank you. The particular case of the configuration is a very good question. So the particular case of the, so you get if S is a polygon with special points which are vertices of this polygon, then in this case A, G, let's call this Dn, disk with n points, this is precisely by definition conv n of Ag. Yes, the definition of this space is such that for the disk you get precisely this. I mean, the way formula is definitely conjecture, so mirror duality, no. Yes, it's a theorem. The set. No. For SL2, it's more subtle. So it's a theorem in general for any group G. It's a theorem that this set is correct. That if you, I can form. It's not. If you take this A G S of ZT, it parametrizes a basis on in the functions on local systems GS. But this is, for SL2 it's better because it gives you the canonical basis. In general, it just tells us that it gives you some basis. For example, this set is right. It has, so to speak, the same size as it needed to be. But then there is, I didn't have any chance to talk about that. There is somehow the story, how you get this basis. And you get this basis going through affine Grassmannian because that's how the Langlands little group appears. And it's part of this is going on the surface smoothly, and some part needs to be done to get the canonical basis. But the very fact that you get some basis, you can prove this from what we get. Yeah, I mean, you have to formulate, if you want it this way, you have to formulate this appropriately. Yes, this is a question of a basis in infinite-dimensional vector space. So what do you mean by this? We can start talking about this, but you can make sense out of this. I'm just somehow saying that it's clear that this set is correct. There's no questions about this. But how it's a theorem that that you can construct linear basis on this vector space parameterized by points of this set. Have a construction. This construction is not the one. Is not the best one, and so it has many downfalls in the sense that it's not producing new canonical base, but produces some basis. No, it's enough to do this. It follows from the fact that you can do this for the disk, and that the instantiation of the disk is cyclically invariant. That's enough. Glue somehow. Yes. Yes. Yeah. What? No, definitely. So I forgot to mention this. Good to mention that there is a paper of Arkady Berenstein and David Kazhdan, which treats a case which is similar to this. Not this, as far as I understand, but no. You treat the weight multiplicities and then tensor. Huh? But anyway, so for three representations, I didn't. You treat tensor product in the tensor products of n representations, right? And as far as I understood, yeah, maybe I just didn't understand. So as what I understand, you treated. Yes. But what I wanted to say is that you have a construction in the there's related problems. You can consider invariants just in tensor products. And there is a canonical basis there, and has a similar description. And this is exactly reduces to what you have. Yes, but in that case, but as far as I understand, this is different. But anyway, so the space, let me just say, that the space which you consider, if you want to consider just tensor products, you do exactly the same construction, but you put one B and many A's. And then this reproduces what you have literally, yeah. But that's slightly different. In particular, it's not cyclic symmetric and so on. Okay.
I suppose this is the basis also is in bijection with crystal.
Definitely, definitely.
So in crystal there is action of some group which is called the cactus group.
Yes.
Which is kind of limit of Pareto. Well, in the limit Q goes to 0, Pareto group doesn't really act, but what acts is cactus group. And it is generated by flips of intervals.
Yes.
And the question is, can you define birational transformations on products of G mod U?
So we discussed this with Joel Kamnitzer, and we were saying that we finished working on this, so we tried to write it together somehow. So there's a way to do it, but this is not part of what I'm talking about here.
So there is a birational map, which on the level of tropical points will produce this action.
Which action?
The action of cactus group on the crystal.
I think so.
And one more question about the module. So do you have explicit differential equations, at least for SL2 or some special cases, which define this module?
Again, so in the situation when I wish I had time to talk about this, you can run the same kind of picture in many different situations. For example, you can consider the simplest one, which you have B and A, and you require that this is in generic position. In this situation, the potential is always defined by using the contributions of the corners. And in this particular situation, this is literally Givental's work. I mean, not that it's similar or that it's literally Givental works. And for GLN, it literally reproduces in these special coordinates this remarkable potential, special potential which we had. And so in that case, because it's just that, so you